walkthrough of homework for Module 3, Part A. I've already posted the solutions to that, and so you can check your answers against the solutions, but I wanted to show you how to use MATLAB to do these calculations. And I want to use MATLAB for doing these types of calculations moving forward, because I think it takes a lot of the tedium out of it, but yet you still understand the basic concepts, hopefully. And so I'll be interested in your feedback on that. All right, so the first, here's the template. It's basically putting the homework into a live editor file. So that's the cool thing about live editors. You can put images and that sort of thing in there to document engineering calculations. All right, so the first problem here is to use the definition of the Laplace transform to show this Laplace transform pair. All right, so we're going to use the symbolic toolbox, and so we have to define symbolic variables. And I'm looking at this, I see a T, an A, and an S, so I put all those in there. And then I realize this, this signal, if I called it lowercase x of t, all right, the Laplace transform is going to be the integral, according to the definition. So INT stands for integral in the symbolic toolbox. And then I put in the integrand. All right, and then I put in the limits of integration. So the definition of the Laplace integral is the integrand. Okay, so I put in the function, and then I multiply by e to the minus s t. Then I put in the limits of integration. That's going to go 0 to infinity. All right, so when I run this, you'll see I get this kind of odd looking result. All right, and so one of the things I wanted to show you is that MATLAB doesn't really understand any kind of constraints on A and S. All right, and it turns out, if you study Laplace transforms in more detail, there's this idea of regions of convergence. All right, what values of S will work for the Laplace transform to converge. Okay, and so here's a trick that you can use in MATLAB. We're going to assume A plus S is positive. All right, and so if I look at this limit here, if A plus S is positive, okay, then I have a negative sign times a positive number times t, and I let t get very large. If that's the case, if A plus S is positive, then this limit is going to go to 0. The exponential is going to dominate the t term, okay? And, this part doesn't depend on t. So if A plus S is positive, I would expect this limit to converge down to 0. If I rerun this, I do in fact get the proper Laplace transform for this particular signal. Okay, so I'd like to go ahead and reproduce that in the work that you turn in, but I just wanted to show you how you can use the integration function within the MATLAB symbolic toolbox to prove this Laplace transform pair. Okay, next I want you to go through just the straightforward, taking of Laplace transform. So one thing you should do is you don't want one answer to corrupt the next part. Okay, so we're going to clear everything and start over every time. And so if I'm looking at part A, I see a symbolic variable that I'm going to need is t, and I usually throw in s because I know Laplace transforms end up being a function of s. Okay, but then it's just typing in the function, running this, and getting the result. Okay, that's exactly the result we would expect to get. Okay, so do that for the remaining parts. Okay, and again, you can reproduce this in your work. All right, so let's move on down. I expect you can easily do parts B and C on this. All right, so let's move on down to part A of the next part. Okay, so again, we're gonna clear everything so that we get a fresh start and one part can't corrupt the results from another. Okay, so Sims, I'm going to do part A here, and in part A, I'm seeing a unit step, and I know that I'm going to have a T variable, an S variable. I'm going to use cap Y. All right, and that should work. That should be enough. All right, and then I'm going to put in equations and use the solve function to show you how to do this systematically. All right, so in this particular case, we actually have an initial condition. I'm going to call that y0. So y0 is equal to 1. Go ahead and put that in. All right, and then I'm going to take the Laplace transform of the equation. All right, and the first equation I'm going to have is for the x variable, and I'm going to define that as 1 over s. Okay, so I say x variable. Now that doesn't even show up in here. What am I talking about, x? Well, the input here is unit step. Okay, so you see 6 us, where us is the unit step function. Okay, so my idea here is I wanted to show you, you can make this a little more general. So what if you wanted to do something besides the unit step? You know, so I'm using the time variable lowercase x of t to denote the input. Okay, so x of t has a Laplace transform capital X. All right, so I'm making capital X be 1 over s. Okay, because 1 over s is the Laplace transform of the unit step. Okay, so from there, hopefully you'll see what I mean. From there, I can write a second equation. All right. So I'm making this systematic so that you can apply this across different types of problems. So my second equation is I take the Laplace transform of y dot. Okay, so that would be s times cap y minus the initial condition. The initial condition in this case is y naught. All right, and then I get to the next variable, 3. The Laplace transform of lowercase y is uppercase y. Okay, and then I have 6 times the unit step, and the unit step is, in this case, stored by the variable x. All right, so that's my second equation. All right. Okay, here's the next step that's a little bit tricky. I'm going to say solve equation 1, equation 2 for y and x. All right. Now it seems a little redundant to say to solve for x, but you know that's the way it's set up to make this work, where I can be generalized enough where I can substitute different forcing functions for this differential equation. Okay, so here's what you need to know. This is solving for 2 variables, but I only have 1 output variable. And what's going to happen in MATLAB is it's going to stuff that answer into a structure, okay? And so it's pretty easy to get, let me just run this and you can see what happens. Yeah. The other thing is, if you have an equation, you know, there's 2 types of equations I'm doing here. EQ2, I'm labeling this equation, but I don't have this set up as a symbolic equation yet. I need a double equal sign. Easy to type. A double equal sign. To properly define that equation. That's why it threw an error, because it wasn't, it was expecting some defining equation, and all I had was a usual MATLAB equation, not a symbolic equation. Double equal signs are needed for symbolic equations. So I rerun this, and it's lost the variable kappa X it's expecting that to be a symbolic variable. Okay. All right. So it's good, to see the errors so that if these occur for you, you can address them. All right. So at this point, I have this structure. You see, it says struct with fields. Okay. So I have a field y and x, and so if I wanted to extract y back out of that, I can see y is equal to s dot y. Remember, with data structures, maybe you don't know this, but with data structures, you can access parts of that data structure with the dot notation. All right, so now when I rerun this, I get capital Y. All right, and so from there, it's just a matter of doing the inverse Laplace transform. And we run that, and we get the solution. All right, so that should match with what you have for the homework solution set. Okay, so please work through this. I'm going to just have you turn in this live scribed script completely filled out. You can put your name on it at the top. You can see I have this set up with the title and submit, put your name here. Fill out the rest of this for homework module 3 part A. All right, so you won't be turning something in on Gradescope for this. It's going to be completely within Canvas. Okay, so if you have any questions, just let me know. I'm here waiting for your questions.